Okay, wow. Welcome to, what classes? Okay, welcome to EE123, lecture 8. Woo! Woo! Just dropping, huh? Okay, so today we're gonna do. Thank you for coming this Friday. Now I'm more conscious to this. It's really annoying. Okay, so FFT. Last time we talked about the FFT. We're gonna finish today, but I also want to talk about Lab 1. You should start reading chapter 10.1, 10.2, which is spectral decomposition. It's not spectral decomposition, but spectral analysis using the DFT. Midterm date is now set to February. Midterm 1 date is set to February 22nd. Okay. Yeah. It's going to be in class, and it's going to be 2 hours. So you should plan. Okay, so it's going to be in class. It's going to be 2 hours. I'm going to design it for 1 hour. We're going to give you 2 hours. And it's going to include also the section time immediately after. It's on Monday. Hence, you have to come. And, yeah. So, and it's going to be in this room. Any questions? Yeah. Open everything. Okay, so except internet and phones and stuff like that. Okay, so that is not allowed. But you can have open everything. I'll talk a little bit more about it later maybe. But I do recommend not to bring everything because it's just going to take you time to look at things up. But just for your, just so you remain calm and you have the confidence that you'll be able to get whatever you need if then I'm going to allow it. I do recommend making a cheat sheet without cheating, to take as a accessory for the exam. Okay. So I want to show you something. Lab 1 is all about a sonar, but I want to show you this project that's called GNU Radio, and like GNU Radio, like the project GNU. This is it was an open source project that just went away. And I can't find it. Sorry about that. Where'd he go? When Windows just disappear? Okay, found it. Okay, so let me just, it's too big of a window here. It's not going to let me. Oh, boy. Yeah, it's X Windows, so yeah, whatever you think about X Windows, you can, either think or not think about. But sometimes it's not so compatible to stuff. Let me try to. Okay, I'll just play it, and I wanted to show you this, but let me just. Oh, great. Yeah, X Windows for you. Okay. Yeah, I'm going to give it one more shot, but if it's not going to work, then I'm not going to show you this time. I'm just going to arrangement, mirror display. Maybe that's going to work. I don't know where it is. Okay, there you go. Okay, so this project, if you can see here, I have an audio source. I cannot figure out right now how to do this, but it's what I've built through. So this project is aimed towards creating a open source SDR, a software-defined radio. So it implements a lot of the all the parts that are needed in creating radios. So different demodulations, different operator, and so on and so forth. It's written in C++ and other types. Its architecture is streaming. So you connect blocks to each other, and then data is streamed between blocks. But there's also a nice Python interface graphical that you can just put these blocks, connect them together, and then it would create the whole application layer from this. So it's quite nice. One thing you can use it for radio, but I use it to create a sonar. And this is a Doppler, so it's a Doppler sonar, where I'm now transmitting audio at a inaudible frequency. Okay, so 19 kilohertz, something like this. Can you hear it? Anybody can hear it? Can you hear it? No, so this is inaudible frequency, okay? For most humans, okay? Now, what I'm going to do then is I'm also receiving that frequency with the microphone, and you can see that as I'm going to move my hand, you're going to be able to see the Doppler. So what I do is I transmit this frequency, and then I demodulate that frequency into DC, and then high-pass filter so you don't see the carrier. So you only see whatever deviates from this. Then on top of that, I've added, I'm taking the signal that's generated here, and I upconvert it to an audio frequency, which you then will be able to hear. Can you hear it? It's like a theremin. So you can play with this forever. But it's pretty nice. And we thought about maybe adding this to the lab, but we decided that instead of doing Doppler stuff, we're going to do kind of reflection. But you can add that. Like that could be an interesting project to add something that can detect both velocity and distance in the final project. Okay. So I just wanted to show you this. Let me just go back to my screen where I do not want to mirror. Great. Okay, any questions about that? The thing is really easy to do this using these tools. Of course, you'll know how to do this in this class. I mean, it's not a lot of very difficult operations, but with very simple equipment, you can create something pretty exciting. People have done user interface, so HCI based on this. So you don't hear anything, but you can like move your hands and use a speaker and microphone in order to interact with your computer. Okay, so there's a lot of cool stuff that you can do. Okay, let's talk about Lab 1. Lab 1 is all about connecting to the audio of your, so playing audio on the computer, receiving it, doing some analysis. One of the things that you're going to learn is to generate a pulse, which is a chirp signal. A chirp sweeps the frequency in a linear. So this is a linear chirp. It sweeps the frequency. You're going to generate one. You're going to learn how to generate one appropriately. But you're also going to then look at the frequency response of the chirp. And as it turns out, frequency response is constant in frequency. It's interesting that a chirp in time is also a chirp in frequency. Okay, so it's quite an interesting phenomenon. It has a constant envelope, so you transmit constant amplitude, and you get a constant frequency across a particular bandwidth. Okay, so with a chirp, the nice thing about it, time and frequency are kind of coupled to each other because at every time point you have a different frequency. Okay, so you have correspondence, like after a second, you'll play a certain frequency, and that will also correspond to the particular frequency that happens. So time and frequency are linearly coupled to each other. So if you play and record a chirp, if you look at the envelope, if you look at the absolute value of the received signal, that's the time signal, and that's its frequency response. Okay, so that's pretty interesting because they're the same. So the frequency response is actually the time signal that you measure. And it kind of makes sense because what's a frequency response? It's a response of a system to a frequency, and we just sweep frequency very slowly. So it's exactly the same. Okay? Right? So there's going to some assumptions are built in here about the system getting into kind of a steady state because we're sweeping the frequency very slowly. If we sweep them fast, then some of these assumptions will fail. Okay, so you have to take that into account. Then after you do this, we will show you how you compute an envelope of a signal, so envelope of the magnitude using the Hilbert transform. You're going to look at that by creating what's called an analytic signal by running your signal through a Hilbert transform and then looking at the magnitude. You'll see what it means. All the descriptions are in the lab. I just want to go through so when you go through the lab, you kind of recall what I'm talking about. The other thing that you're going to look at is the autocorrelation property of a chirp. So a chirp, an autocorrelation is like a convolution, only you don't flip the signal. Okay? So for symmetric signals, this is actually exactly the same. And so you're going to compare the autocorrelation of a chirp to a pure frequency pulse. Okay? If you look at the magnitude of the autocorrelation of a pure frequency pulse, it kind of makes sense. It's a rect, kind of over time that's modulated. And if you do an autocorrelation of something that's rectangular, you get a triangle, right? So it's going to be very broad. Okay? So you send a pulse of 1 millisecond, its autocorrelation is going to be spread out across 2 milliseconds, but also the full width half max is going to be still 1 millisecond. Okay, so it's going to be spread out. But instead, if you actually use a chirp, it has the property of what's called pulse compression. It has a narrow autocorrelation. So for the same time that you're going to play a chirp, if you look at the autocorrelation is going to be much narrow compared to a pure tone. Okay? And if you increase the bandwidth of the chirp, so if this is a 2 kilohertz chirp, so you sweep over 2 kilohertz of frequencies, if you sweep over 5 kilohertz, it becomes more and more narrow. Okay? So if you increase the bandwidth, the autocorrelation becomes narrow and narrow. And this is an interesting property that allows you to play a long signal, but then still keep the resolution when we talk about radar. Okay, so if I send a pulse, a short pulse, and things are coming back, if the pulse is short, I'm able to detect differences between two targets that are close to each other. But the problem is that I don't have enough energy. I'm going to be limited by how much energy I'm going to put. I can actually play a longer pulse, but have the property of pulse compression in order to keep the resolution, be able to distinguish between close targets, but then transmit over a longer time. Okay, so you're going to look at this. Once you generate all of this, you're going to generate a function which generates a pulse which is analytic. Analytic means that it's basically instead of having a cosine, you are going to generate the complex exponential of it. Okay, complex exponential version, just one-sided spectrum, as opposed to a two-sided spectrum of a chirp. Okay? So you're going to generate this, but only play the real part when you actually send it. You're going to transmit and record a series of chirp pulses, okay, or pure frequency pulses. And when you play them, these are the pulses we play in green, and the pulses we receive are in blue. They have some delay due to the system, but overall, if you think of where my microphone and speakers are, they're pretty close to each other. So this is a system delay between this and this. But after that, all these small wiggly stuff are reflections that are coming back from the room. which is pretty cool. What you're going to do then is you're going to look at one of these pulses that you get back, okay, one of these sections, and so you're going to send something like this, which is a windowed chirp or a windowed frequency. And then when you receive it, you're going to see kind of what's called a feed-through, which is the speaker directly, in the shortest path getting to the microphone. But you're also going to see reflections from different places in the room, okay, which is pretty nice. After that, you're going to be filtering with the match filter, which it's the analytic version of it. Take the magnitude, which will give you the envelope, and then you'll be able to see exactly where those reflections are. Okay? So that's going to enhance your detection by performing this, what's called an operation of match filtering. Match filtering is an autocorrelation with exactly what you sent. And you're going to go over that. Okay? So now if you plot this over time, you effectively you can see kind of where reflections happen. Okay? And then the last thing you're going to do is, once you have all these functions, you're going to put them together in we wrap for you kind of a real-time interface where you would be able to generate things like this, where you play these pulses, and in real time you can move something away from the computer and be able to see how far these reflections are. And those are based, of course, on the speed of sound. So for a particular temperature in a room, there's a particular, speed of sound, and you can then transform the time that you receive things into distance. Okay? Let me just show you a demo just to kind of see so you can see what it actually means. So this is all going to be in IPython, and I hope this thing works because it never works when I do a demo. You know what cytons are? I mentioned that, right? Cytons are these particles that eyes emit and interfere with the demo. Oh. Okay, so all kind of the stuff you see here is reflections in the room, but now I'm kind of moving the book. The thing is that this particular Mac has the microphone on the side. So what I do recommend when you do these type of experiments is you can put something here, like your hand, and make sure that the microphone is more directional and sensitive to other places. So if I move the whole thing together, you see how the reflections are moving. And those are reflections from 2 meters and 2.5 meters away. See, as I move it down, right? It's probably, I'm not sure actually where it's coming from, but anything that's 2.5 meters away. So on a ceiling or maybe the corner or somewhere else. It's not so directional. So the performance of this thing is going to depend on your laptop. So it'll vary, but you'll definitely be able to get something. So that's, we think it's pretty cool. And the one thing I wanted you to play with is, of course, the parameters of the chirp that you send, and you can change them and see the differences in resolution that you can resolve things, differences in intensity, and so on and so forth, versus the length of the pulse and the bandwidth that you're going to play, and so on and so forth. Okay? Any questions? No questions? So this is we think it's a really nice lab. Questions? It is position.
Aren't you measuring the distance from your microphone back to it?
No.
Which direction it's coming from?
No, it doesn't measure position from microphone. Whatever you send reflects from the ceiling, for example, or from other places in the room, come back to the microphone, and that's what you measure. You measure those reflections. We don't, because it's not directional. So if you had, you can hook up like an external sound card, like a USB one, with a microphone and speaker that are actually directional, and you'll be able to do this, in a directional way, if you really wanted to. Yeah. So this is more isotropic, and depends on kind of what this particular system you have. Where's the microphone? Where's the speaker? I do recommend only using one of the speakers, not both of them, because they can interfere with each other. So put that on the left speaker, or the speaker that's closest to your microphone, then the performance will be better. If you wanted to do something directional, you just need to have a speaker and a microphone that you just, put them in a cone or something that would only be sensitive to a particular direction, then that's be more directional. Yeah. Does this make sense? Okay, so where were we before? Oh, you want this? Oh, yeah, FFT. So you remember the FFT? All of this is because you are able to do the FFT. Okay? So let's go back and kind of describe what we did when we did decimation in time. For decimation in time, you at every step, okay, you break the FFT into smaller sizes FFT, okay, smaller sizes FFT, and then combine them by multiplying, the odd parts with some twiddle factors, add, subtract to the DFT of the even parts. And then you take those and decompose it again, and decompose again, and decompose again. And all it comes down into just additions, subtractions, and multiplications with the twiddle factors. That is it. Okay? And if you look at these decomposition, of course, at every step you do n operations. And how many do you do? N log n. Okay, a log n type operation overall. So in general, again, there's log 2n stages. Each stage requires n over 2 complex multiplication. Some of them are trivial. Okay, some of them just multiplying with 1 or multiplying with minus 1. The total number of complex multiplication, then you can count to n over 2 log 2. Okay. So so the one thing that you have to worry about is the following. If you want to have this calculation in place that would yield an output which correspond to an order output of the DFT, you need to reshuffle, shuffle your input such that it will fit to the particular output. Okay? And so you have to reorder this in order to come out with a nice tree that leads to this solution. Okay? So if you think of what you're actually doing, this permutation, at the first stage you split into odd and even. Okay? So you take the 0 low order bit first. Okay? If you think of what are you actually doing, if you look at look at the 8 numbers represented in binary, okay, what is even and odd? You're just looking at the 0th low order bit, and you split them into 0 and 1s. Okay. The next stage, you do that for the next binary 0. The next stage, you do this for the next binary 0, and so on and so forth. So really, what you're doing is reversing the bit order of those indices. Okay? That's actually what is being done in that order. So if you look for n equal 8, if you have decimal from 0 to 7, if this is the binary, then the bit reversed array would be this. Okay, you just flip the order of the bits. Okay? If you flip the order of the bits, you get the bit reversed decimal, which is 0.4261537, which is exactly 0.4261537. Okay? That will end up. So a bit reverse order will give you an ordered output. Okay? Does this make sense? Okay, so then we did this by splitting the inputs, right? The inputs of the system, reordering them by even and odd, and then doing those operations. Okay. But there's other ways that you can also implement a similar decomposition, and the other one that I want to talk about is the decimation-in-frequency fast Fourier transform. Okay. So we're going to go quite briefly on it, but I'll just show you the key ideas there. Again, if you look at the DFT equation, okay, DFT, you sum over 0 to n minus 1, x of n, w sub n to the nk. Now, before that, we looked at the even inputs and the even outputs, right? And we split that sum into even inputs and even outputs. No, I didn't. I split the sum into an even inputs and odd inputs. Okay? Okay? All right. So what we could what if we look at the output then and ask ourselves, well, what if we just look at the odd outputs and the odd inputs? What does this correspond to? Okay. So if we only look at even samples of xk, we can rename x to be rename k to be 2r. So x of 2r, what will be then corresponding to? It's going to correspond to n equals 0 to n minus 1, x of n, w sub n, and just 2r. So that's great. Okay. Now we can split these two sums over the first n over 2 samples and the second part of the n over 2 samples. So now I have half the sums. N equals 0 to n over 2 minus 1 of that, and then n equals 0 to n over 2 minus 1, and then n plus n over 2. So I just split the entire sum into the first part and the first part of the samples. Okay. So what is interesting about this is now you've got this something to the power of 2, and the sum to n over 2. But we know that this is also the same as w sub n over 2. If we do that, what does it look like? What is it going to look like? This is sum over like a smaller sequence, right? This is a sum over a smaller sequence. What's inside of the sequence is n over 2. Then we can express this as w sub n over 2, and hence you've got yourself two DFTs that are summed together. Two small DFTs that are summed together. And so this is what we want to reach at the end. Okay? We want to reach that point. Okay? Okay. So w sub n to the power of 2r, n plus n over 2. You can just take this n over 2 out, multiply by 2r, and you've got w sub n 2rn, and then w sub n to the power of n. W sub n to the power of n is 1. So I'm just end with this. So it's w sub n to the power of 2rn, which we know that we can take this 2 and poop, drop it down to w sub n over 2 to the power of rn. Okay? So this we're going to use this trick a lot. Okay? So now we've got ourselves the sum over of the first part, the sum over the second part of the sequence. And now we're going to use this property by replacing this with this, okay, by this relationship. Okay, so I haven't really done much. Just replace this with this. Now, stare at this. What do you see? I see we multiply by w sub n to the power of 2Rn. I see something multiplied by w sub n to the power of 2Rn. This is the same factor. You just sum over different values. So I'm going to take this factor and take it out, and then sum these two together. Does this make sense? So this is multiplied by that. This is multiplied by the same thing. I can take it out and sum x of n plus x of n plus n, which shows up here. Okay, I'll let you digest it for a second. X of n appears here. X of n plus n over 2 appears here. Brackets, multiply by that. But wait a second. I know that this, I can take the 2 and dump it down. So I dumped it down. And now, ha! I know what is this. I know. What is this? It's the DFT of what? Of that sequence. Right? It's the DFT of x of n plus x of n plus n. Okay, so if I want to compute the DFT of the even values, so the even indices of the DFT, what I do is I combine my sequence with the first half of it, the first half with the second half, and then compute the DFT of it. Cool. Right? Yeah. Thank you. I didn't really get what you were going to say, and I was kind of dozing off, and I apologize. Okay. So if we want to compute the even indices, we can compute a DFT of n over 2 of a sequence which is the sum of the first part, the sum of with the second half. And then as it turns out, you can also derive it for the odd values. And for the odd values, if you want to compute the odd indices, it's still a DFT of n over 2, but now you just subtract them and then multiply by a 12 factor. Okay? So you can show this. I'm not going to go over this. So similar argument will show this. So now we can calculate the DFT, right? We can calculate the DFT for the even indices and the odd indices by smaller DFTs. And then what do you do? Well, these are DFTs that are small, right? So I can take the DFT that are small and then calculate that by taking the even indices and then summing over, those parts, adding to this. So again, divide and conquer, right? So I can compute these small DFTs, these ones, in the same way. Look at their even and their odds. Look at their even and their odds. Decompose them. And then do it again and again till I reach nothing. The smallest that I can't decompose it anymore. Okay? So that's pretty cool. Well, that's revolutionary, right? I mean, that's probably better than decomposing the inputs, right? So as it turns out, it matters not, because here's what basically it does. If you look if you look at this, this is the tree that we end up decomposing to. Okay? Every time that we do this. This is the tree that we ended up decomposing. And if you look at that tree, you kind of stare at this. Basically, it looks exactly like the decimation-in-time algorithm, but just reversed. Okay? So input are in normal order. So now your inputs are normal. The outputs are flipped, because every time we decompose into even and odds, remember? The output we decompose in even and odds. So now it's bit reversed in the output. The input is the same. The output is bit reversed. And then all the arrows are just pointing the other way. And that kind of makes sense, because who cares if it's a forward or inverse DFT? It's the same. Okay, so you can do the same decomposition doing that. And whether to use this or the other, I don't care. Okay, it matters not. It depends where you want the end to. If you do want to reorder first and then do this, or you want to do it afterwards. Okay. Questions? So you got a question in one of the homework that kind of leads you to this. So to the same approach. I found it. Okay. So a similar argument you can apply to arbitrary length of DFTs. Okay. So now you can also do, let's say you have an n equals 6. Then you can do a decimation-in-time FFT that would compute 2-point DFTs followed by 3-point DFTs. Okay? So you don't have to decompose into 2 parts. And it depends on the size that you have. Yeah, if you have a size of 6, it's not binary. It's not a power of 2. Then you can't really decompose it in exactly the same way. But you can decompose it into either 3 2-point DFTs followed by a 2 3-point DFTs, or decompose it into 2 3-point DFTs followed by 3 2-point DFTs. Okay, so there's all these options that you could do in order to do the implementation. And one of the homework that you're going to get, I think, is something like that. Yes?
If you take the prime number DFT, you're basically just slow way.
Prime numbers are very problematic when you want to do fast operations. Absolutely. But the cool thing about it is that you just zero pad at 1 and you're good. Right, but prime numbers are difficult in general. And I'll actually show you some examples. Okay, so what people have done is they said, okay, well, often it used to be that everybody would just do DFT, FFTs of size, powers of 2. That was the first thing, because there was such an implementation, and they're just using this over and over and over again. And if you didn't, you always zero pad to the next power of 2, and then you just did a DFT power 2. It's called radix 2 type of DFT. Okay, that's the if you hear it, this jargon is radix 2. But then people have realized that, well, okay, what about different sizes? Sometimes you don't want a zero pad. Sometimes you want to maybe take other advantages for particular sequences and and compute things much faster. So, for example, there's a lot of nice components are available up to the length of 20 or so. People have optimized that part. So up to DFT of 20, you know how to do the small operations very efficiently. All those factors, up to 20. I think now even maybe more than this. So that you can optimize those parts. Once you have those parts, then all you need to do is take a large number and decompose it into these factors. once you have these factors, you can take these efficient implementations and use them. Okay? So one example is it's what's called a radix 4. Okay? A radix 4 decomposition. And a radix 4, a lot of things that you'll see a lot of multiplications there that are with a twiddle factor that is w sub n to the power of n over 4. Okay? Because that's the last one that you're going to reach. The smallest 4-point kind of DFT. In that case, multiplying by this is really multiplying by minus j. But multiplying by minus j is really not a multiplication. Okay? And that's a nice thing. All you need to do in order to implement a multiplication by minus j is to swap the real and imaginary component of the complex number. So that's pretty cool. You just move memory instead of performing an operation like a multiplication. So it is more efficient to do this. So all these tricks people have used in order to do these DFTs. So DFTs of length 4 don't require any complex multiplies. Pretty cool, right? Half of the one for 8-point also don't require multiplication, and so on and so forth. So if you look at these composite length DFT, they can be much more efficient for the factors you can decompose to. And here's an example. If you look at n equals 693, that's factored into 7, 9, and 11. And so you can kind of find an implementation which either does 9 times 11 DFTs of length 7, or 7 times 11 DFTs of length 9, and you can figure out which one is the most efficient for this particular case, for the architecture that you have. And that's where FFTW, which is a package that was developed at MIT, came into place, and they realized, wait a second, when you compute an FFT, so FTW stands for the fastest Fourier transform in the West, okay. And what they realized is that, wait a second, implementation really depends on architecture. Your architecture of your computer, how much cache you have, right? It's really important. What's the size of it? So all the small details of how memory and how things are implemented inside the processor make a huge deal when you actually think about the real computation that happens. So you can say, well, yeah, I have less complex multiplication, let's say if I do radix 2. But the thing is, that's not necessarily exploit the architecture the best in terms of locality of operations. And so what they realize is, okay, so why not try them all? You have a certain size that you want to compute FFT over and over again. Let's decompose it to all possible sizes. Try it. Try it on the particular architecture, the computer that you have. Run it. Measure the times, and then store a file that tells you if you call that size again on that particular computer, you would use those sizes because that's the most efficient for this particular architecture. And that changed the game. And of course, they come up with all those. So maybe you don't want to go and train all these options. So there's heuristics that they use and so on and so forth. But that really changed a lot of things in the industry. And I think MATLAB uses FTW since like version 6. Of course, NumPy that you're using here in the class also uses FFTW in it. The nice thing about this is that it has 2 licenses. One of them is a license that everybody could use. So if you're not using for commercial use, you can use it. If you are going to use it for commercial, then you have to license it. Okay? So if you're going to make money out of it, you need to license. Otherwise, you don't. But here's where things are kind of interesting. Here's an example. This is a 3-year-old simulation experiment that I ran using MATLAB by computing FFTs with different lengths. And you see that it varies in terms of the performance. And so normally you would say, well, 256 should have been, pretty fast, right? But actually 224 is faster than 256. And 192 is actually faster as well. And 288 is pretty close to 256. So if I used in the past, let's say I had a 257 type of sequence, in the past I would have gone to 512 in order to zero pad it to 512 in order to do the computation, but I can just as well do it with I think it's 258. So just zero pad by 1, and I can do it just as well by coming with different decompositions. And this becomes a bigger deal as you go for larger and larger and larger sizes. Okay? You see these fluctuations coming. And this is because of the architecture of the computer. Okay? And that's where, computation is not only now thinking from a mathematical point of view of just thinking about, I need to do that number of operations, but you also now think of locality, of, how you load things into cache, such as coherence, so you don't have to call it again. And so all the stuff that you guys learn in 61C plays a big deal here. And so the computational thinking from not just the number of operations mathematically, but also thinking of how you're going to implement it makes a big difference. Avoid communication and other things like that. Okay, so in the last part, last 3 minutes, I want to show you, again, the FFT as a matrix operation. So if you look at it from a matrix point of view, it's full, it's dense. The DFT matrix is dense. Okay, but you can also, as it turns out, decompose this FFT matrix to these type of operation. What is FFT? Is you first permute things by either even and odd, so a matrix that does these permutations. Then you multiply by those twiddle factors. Okay? And then you either add or subtract them, right? So these are diagonal entries. And so effectively, if you look at an n equal 4 type of FFT, this is the permutation, this is the add, subtract, the butterfly operations, and these are the twiddle factors. Okay? And so now the matrix that was previously dense can be decomposed into a multiplication of sparse matrices. And that's why it's really fast. Okay? And you can think about that also when you have now an operator, you can maybe decompose it into series of sparse matrices that can implement things fast. Now everybody knows about the DFT. They know that they're that it's log n log n type of operation. But let's assume nothing about your signal. Right? Assume nothing about your signal. I can take any signal, noise, and compute an n log n type of operations. And so more recently, people have been thinking about things like sparsity. What if my signal is redundant? What if my signal has only a few frequencies that I want to calculate? Do I really need to go and compute an n log n type of operation to get just 3 frequencies? Does this happen? Obviously, because if often I would like to measure a particular frequency. Okay, so I do an DFT over the entire thing, and then I get a result n log n. But really, do I need to do this? If I'm going to look for this one frequency or just a few, do I really need to compute all this stuff? And so there are some work that shows that you can do this and go well below n log n. And if you have k sparse frequencies, you only need to have computation of the order of k log n, where k is the sparsity. Okay? And so this is just an example where you look at this is a sparse FFT versus the signal size. It does not increase with the signal size. But it does. But if you look at the regular FFT or FFTW, it increases with n log n. Okay? And if you look at how sparse it increases, so the sparse FFT does increase almost linearly. But then here's the caveat: when you reach a certain point, it's going to be more expensive than the regular FFTW. But that point is still, so if your sparsity is less than, I think, 2 orders of magnitude here, then it's still worth doing this. But if your sparsity is beyond that, then it's not worth. And you might as well just do the full FFT. Okay? Yeah. Well, so near optimal is that they can actually bound. You'd like to have it k log, but like it's almost. I think so, yeah. K log k. Well, probably not, because you have an n. If it's noiseless? Okay. Yeah. All right. Have a nice weekend. There's new homework going to be posted tonight. Homework's due tonight. Work on the lab. It does require work and time. So spend time on the lab. Come to lab office hours too. Yep.
So apparently the microphone on my computer